Today we would like to show you the usage of the virtual clamping technology for automotive hang-on parts. The goal is to avoid multiple measurement loops which are typically needed because of the adjustment of the fourth point. The first example would be a front hood. Front hoods are typically measured on mechanical fixtures with 4 support points, and one of these 4 points can be adjusted. When the hood is correctly positioned on these support points, the measurement can start. The special thing about the evaluation of the front hoods is that the alignment of the measurement data to the CAD model is done by the outer shell of the hood only. This is because it is wanted to simulate the latter assembly situation where the flush and gap to the fender, for example, define the visual impression of the part. As we can see in the results, there is an unwanted deviation at the fourth point. Now, the user would have to readjust the fourth point in order to come closer to zero. A lot of experience is needed to choose the right amount of lift at the adjustment point. In general, multiple measurement loops are needed until the deviation of the fourth point finally comes close to zero. With our virtual clamping technology, we do not need these manual iterations. We need only one measurement. The physical loops are replaced by mathematical algorithms and iterations. We call it indirect virtual clamping, as the point where we read out the deviation and the adjustment point are different. As our method is based on FEM algorithms, of course the question arises, how accurate is it and how comparable to the physical process? We did multiple comparisons and we were able to prove that both results are identical if some basic conditions are fulfilled. For example, the hood always has to rest on all points. This is quite crucial. The hood should not be too much distorted. If we take into account an adjustment range of, for example, 1 millimeter, then we could prove that the model error we introduce is approximately 5 to 10% of this adjustment hub. Meaning, with an initial deviation of 1 millimeter, we bring in a model error of maximum 0.1 millimeter. This is a good result because in the physical process, you always have to take into account the stop criterion, which typically is like 0.1 or 0.2 millimeter. This means in practice we are even more accurate with virtual clamping. We can apply the same strategy to other automotive hang-on parts like trunk lids and doors. Also here we need only one measurement. We do not have to clamp or adjust, and thus we can use very basic, cost-effective and simplified holding fixtures. With virtual clamping for hang-on parts, we can save a lot of time and thus easily saving like 20 or 30 minutes per part. The proposed solution consists of an ATOS scanner in a scan box using our multi-part fixture, for example, to hold a large variety of hang-on parts, the GOM-Inspect software and the virtual clamping add-on module. So the method is completely integrated into our parametric kiosk concept, meaning that the user just has to select the template, press one button, and then everything runs automatically. The measurement and the evaluation. At the end, you will see the unclamped and the clamped state without having any manual adjustment or interaction.